Okay, so one more video I'd like to show you this morning. So Huygens says that light is a wave. Okay, so this is it's sort of an important historical moment because like we have these two proposed theories for light, one that it's a wave or one that's a particle. Well, one thing that is a unique characteristics of waves is what happens when two waves meet, when they sort of intersect each other in the media. Okay, in a rope, maybe traveling in opposite directions, that kind of thing, and they cross over each other. What happens? Well, with this thing called interference. Okay, now if Huygens is right that light is a wave, then it should be possible to see interference of light waves. And if he could show that light waves do interfere, then it's case closed and curtains for Newton's particle theory. Okay, that theory would have to be dead in the water because you just can't explain interference if light is a beam of particles. So like for example, if we're throwing snowballs at each other, okay, those are beams of particles. So if I'm throwing one snowball after another at you, okay, and you're throwing them back at me, what would happen if two snowballs were to collide in midair? Well, they definitely would not pass through each other, right? What would happen is they would sort of go splat, right? And you would get a collision. And we know how to deal with collisions with particles that have mass. We did that in the momentum unit. Well, when waves meet, they don't go splash. They don't go, they don't splatter. They don't have this conservation of momentum thing going on in a traditional collision. They actually pass right through each other, okay? But when they meet, you get this phenomenon called interference. So here you see these superposition of two waves traveling in opposite directions. You get a blue wave and a red wave, if you like. You can see it sort of underlined underneath. Blue wave's a little smaller, okay? And then when they meet, you get this phenomenon called interference. So here you can see when they meet in the middle, they form what we call a supercrest. So it's constructive interference because two crests. And the supercrest only exists at the point of intersection, so we call it a standing wave. Okay, so it just seems to be in that one spot. It doesn't move left or right. So there's no lateral movement in the supercrest. It's right there, and then it's gone. Okay, and then the waves just go on their merry way in opposite directions, right? So what's happening is you get a interference where waves meet, okay, and then they pass through each other, and this is very different behavior from a stream of particles. So like two squirt guns, they're shooting streams of water particles. If the streams cross, there's splatter everywhere and this collision that takes place. Well, that's not what should happen if two beams of light cross, if Huygens is right and light is a wave. Okay. Here's the problem for Huygens though. At the time, 300 years ago, there was no clear examples of interference, at least that they recognized as interference, okay, of light waves. So there were some examples, but unfortunately they didn't realize it was interference. And so it was considered a major weakness of Huygens' theory was that no one really ever observed interference of light, or at least recognized it as such. Okay, now I want to show you what happens when you get periodic waves. This is kind of cool. When wave after wave after wave are interfering with each other, then all we see are standing waves. And so what you're seeing here is alternating supercrests and supertroughs. And we looked at this when we did the sound unit for some of you, okay, in grade 9. Okay, so this is interference of waves. I would show you this demo if we were doing it in person. Really cool how that works in a string, let's say, with harmonics and strings. But anyway, this unit is about light and not about sound, but sound is definitely a wave. Okay, and if light is a wave too, it would have similar properties. So interference, crucial. Huygens needs to demonstrate that light does interfere if light really is a wave. Okay. All right, so anyway, you can see this. There's different patterns here of interference, but you get the whole point, right? So when crest meets crest or trough meets trough, we get what's called constructive interference, and the waves like reinforce each other, and you get super crests and super troughs. But some spots, like this point here that's not moving at all right here, okay, that's called a node. That's where you're getting crest meeting trough all the time, and they cancel each other out, and you get destructive interference. Okay, so this is called a standing wave pattern, and it's a result of interference of waves. All right, so that's it for this.